Hello, this is Math 2270 from the College of DuPage, summer 2020, and we're continuing the discussion of introductory matters, definitions, and such. Any function phi defined on an interval I and possessing at least n derivatives that are continuous on I, which when substituted into an nth order differential equation reduces the equation to an identity, is said to be a solution of the equation on that interval. This is the same thing it always means. You plug it in and it works. First example, show that this is a solution to this differential equation for x greater than 0. You know what to do? Let's see how you did. Well, you need to take the first and second derivatives so you can plug them into the left-hand side of this equation. You also plug y into that side. You do the arithmetic and you get an identity. It is the same on both sides. So that does satisfy the differential equation. We did need for x to be greater than 0, so this thing does exist. Now, there are many solutions to that differential equation we just looked at. This is a solution. These two are solutions. And in fact, this last one is also a solution. Serious students may want to verify some of this, particularly this final one. It can provide insight into results yet to come in this class. All right, so here we have another example where we're asking you to show that this is a solution, but we have two initial conditions, which are this for the function itself and this for the first derivative. You know what to do? Let's see how you did. Well, the only thing that you really need to do on this one is we already showed that this was a solution, so we just have to show that it does satisfy the initial conditions, and it does. So soon, or actually we've already talked about this, we'll call this an initial value problem where we have a differential equation and some initial condition. Here's another problem. Show that this, where c is some constant, is the general solution to this differential equation. You know what to do. Let's see how you did. So we take the first derivative to get this, and we substitute it into this differential equation right here, and we see that it is equal to 3, so it is a solution. Now here, I'm asking you, what is the actual solution to this? Now this is the same differential equation we were looking at before, but now I'm giving you an initial condition. I'm saying that y at 1 is equal to minus 4. You know what to do? Let's see how you did. You plug it into the, well, we know what the solution was from the previous problem, so we substitute t to be 1 and y to be minus 4, and we find out that c has to be negative 19 over 4, and that means that this is the solution to the initial value problem. We're to show here that this expression is the actual implicit solution to this differential equation and this initial condition. Now, when we say implicit, means we're not solving for y. We're just trying to show that this does satisfy both the initial condition and the differential equation. You know what to do. Let's see how you did. Now this does require you to do implicit differentiation over here, so you get this, and then you solve for y prime, and y prime, the 2's will cancel, and y prime is exactly equal to t over y. Now, when we also check to see if this expression satisfies y when t is 2 is equal to y is minus 1 when t is equal to 2, we see that when we substitute those values in, it does satisfy the equation. So that is an implicit solution. Here, you're being asked to find an actual explicit solution to this. That means you have to solve for y, the same initial condition. You know what to do. Let's see how you did. So here you have to solve for y, and you conclude that when you take the square root, y is equal to plus or minus the square root of t squared minus 3. But now that we have this explicit solution, we know that the initial condition telling us that y has to be negative tells us that this sign must be negative. See you in section 6.2.